Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 37. Today we will look at a few other variants of the common source stage amplifier and see what properties they possess. Before we go there though, let's take a look at what we covered last time. In lecture number 36, we arrived at the basic common source stage after many trials and tribulations, and we saw that it consists of a single device whose input is applied to the gate of the device and whose output is taken from the drain. That is the definition that we have for the common source stage. And we saw that if we neglect channel length modulation, the voltage gain of the circuit is just given by minus GM of the device times the resistance tied between drain and AC ground, minus GMRD. If we do include channel length modulation, then the resistance tied between the drain and ground includes this RD and this RO in parallel, so we end up with that equation. So this is the important result that we need to memorize for a simple common source stage. Now, on another topic, we looked at the concept of port impedances, and we said that to find the impedance looking into a port means two nodes of any circuit, we have a certain procedure. The procedure is that we go inside that circuit and any independent source, current source or voltage source, that is attached to that circuit or exists inside that circuit should be set to 0. And then we come from outside and apply our own independent voltage source, as shown here. We call it Vx, for example. And we measure the current drawn from this voltage source, Ix, and then Vx over Ix is defined as the impedance or resistance seen at this port or between these two nodes. This procedure is very important to remember. You have to set all independent sources that are inside or outside the circuit attached to it to 0, and then apply our own independent source between the two nodes of interest or the port of interest. So today we will exploit this concept to arrive at a bunch of interesting results. All right, so before looking at the other variants of the common source stage, we will spend a little bit of time on building some current sources out of MOS devices. We have seen this briefly in the past, but this time we will formalize it so that we can understand how a current source is formed and then use that in circuit design. As we will see, we can use that current source in some of these common source stages. All right, so let's look at some MOS current sources. So let's build a current source. Okay, how do we build a current source? Well, we do remember that if a MOS device is in saturation, its current is relatively constant. So here's a MOS device. And we need to bias it to have a certain current in it. So here's the bias voltage applied between the gate and the source. So some amount, call it V0. And what we know is that we have a current source between these two terminals, provided that device is in saturation. So what we do remember is that when we plotted the behavior of this circuit, we applied the voltage between the drain and the source, and we varied the voltage. We saw that initially for low VDSs, the device was in triode region, but once we entered saturation, the current was relatively constant. Remember, 1/2 of mu n C ox W over L times VGS minus VTH squared if we neglect channel length modulation. So roughly speaking, this is what we have observed, ID versus VDS, something like this. Now you want to include channel length modulation, there's a bit of slope. If not, the slope is 0. Okay, so this is an approximation of a current source. An ideal current source is one whose current is constant regardless of the voltage across it. And from here to here, it's a good approximation. So we will use this as a current source. So equivalently, for our purposes, we can say that this is similar to a current source, a constant current source. All right? Okay, now, one interesting point about this implementation is that the current can start from here and only go to 0, at least as far as the equivalent circuit is concerned, only to ground. So this is hard wired to ground. We cannot have it go anywhere else in this equivalent circuit. So it is very difficult to build a current source that goes from one node, one arbitrary node in the circuit, to another arbitrary node in the circuit, if we are looking for constant current sources, such as bias current sources. So we cannot do that. This current source only goes from an arbitrary node in the circuit to ground. It cannot go anywhere else. All right? Okay, so that's what we have. Now, in some cases, we would like to have a different type of current source. What we are looking for is this. We have an arbitrary node in the circuit. We would like to have a current source that goes there, like so. It wants to flow into the node, not out of the node. All right? So the question is, how do we build a current source that flows into a node? And it turns out that when we do this, this end ends up being VDD in the equivalent circuit. But the key point, the key difference between these two is that this is flowing out of the node, this is flowing into the node. Well, okay, so the polarity of the current has changed. And that says maybe we should go from an NMOS device to a PMOS device. So let's do that. We take a PMOS device. We bias it properly. So for example, if we have VDD here, we just connect a battery between VDD and the gate, some voltage. And again, this becomes available as a current source, right? We have only two terminals here. This becomes available as a current source. And it has the same situation, at least if you look at the absolute values. So if you look at the absolute values of ID and VDS, it's the same situation. So these are both good approximations of constant current sources. The only difference being that if it's implemented using an NMOS in such a form, then the current is flowing out of an arbitrary node in the circuit to ground. And if it's implemented out of a PMOS device, as shown here, then it flows from, equivalently, from VDD to an arbitrary node in the circuit. So we can use both of these, and we do use both of these implementations. All right, so remember that, and now let's do a quick calculation on these things. Okay, so we said that this is an approximation to a current source. An ideal current source would have a flat current here. But now, because of channel length modulation, it varies a little. All right, so let's try to construct a realistic circuit for this one and for this one as far as small signal operation is concerned. All right. If this is an ideal current source and is constant, in small signal operation, this would be an open circuit, because a zero current source is equivalent to an open circuit in both cases. So that's easy. But given that this is not an ideal current source, there's a bit of slope here, we would like to see what the equivalent small signal model of this circuit would be. All right, shouldn't be that hard. The first point that we observe is that this is a two-terminal device. If we put everything in a black box, it's only these two terminals that are of interest to us. So we are hoping that the equivalent small signal circuit also has two terminals. What could that be? A capacitor, an inductor, a resistor, maybe a resistor, right? So maybe this will reduce to a resistor. We'll have to see. And similarly here. Okay, so that's what I would like to do. And now I remind you how we found the port impedances. we have a two-terminal device. If it's a two-terminal device, it probably has just an impedance and nothing else. So we would like to find the impedance between these two terminals. And we know how to do that. To find the impedance, we go inside the circuit and set all independent sources to 0. So this guy becomes 0. Okay, that's an AC 0, right? And we draw the small signal model of this guy. Then we come from outside, apply Vx, measure Ix. Okay, so let's do that for this one and see how it goes. So small signal model. I will take that. I start from the left side. I see a voltage source that's constant, so it doesn't change with time. Therefore, it changes 0. Therefore, small signal model of it is 0. So that's a short circuit right here. Then I draw the small signal model of the device. So we have V1 here, GM V1 here, and the source terminal is connected to the battery and to the outside. And then because I am interested in this variation, in the small signal model, I have to include RO, because that represents channel length modulation. So I add RO here. This is the small signal model of this entire circuit. And it has only two terminals sticking out. Now, to find the impedance between these two terminals, we have a method. Our method is bring a voltage source from outside, call it Vx, apply it to these two terminals, and measure the resulting current Ix. Vx over Ix is defined as the impedance seen into this port or between these two nodes. Very well. Can we do that quickly? Well, how much is V1? V1 is 0 because we put a short circuit here. And that makes sense because V1, little v1, represents the changes in the gate source voltage. But because we have a constant battery, the gate source voltage never changes with time, so V1 is 0. V1 is 0, GMV1 is 0. If a current source is 0, it's an open circuit. So this is gone. So what do we have? We have only RO left. So we don't even need to write KVLs and KCLs. It's just obvious that the circuit reduces to RO. So we say Vx over Ix is equal to RO. In other words, if I want to represent this device by small signal model, let me change the color of my pen. If I want to represent this by small signal model, it's just this. Okay, I hope these are not confusing. This is for bias calculations. This is for the small signal model. Okay. All right, so you can see that this would be the same thing. This would also be equivalent to RO of this device with this terminal available going to our circuit, and this terminal going to VDD, this line, which is ultimately AC ground. You know that VDD becomes AC ground when we go to the small signal model. So that's also AC ground, really. So the key point is that anytime we see a MOS device operating as a constant current source, we can, for our small signal purposes, replace it with a single resistance equal to RO. So that's a great simplification, because if you can identify in a given circuit some MOS device is operating as a constant current source, there's no signal anywhere, or we don't have a signal going through the gate or anything, right? It's just a constant current source. We can readily replace it by RO. And the situation is even simpler if we neglect channel length modulation, because then RO goes to infinity and the circuit is equivalent to an open circuit. All right, so that's the nice result that comes out of this analysis, and we will exploit this in the next circuit that we study. All right, let's go ahead and look at the next common source stage that we will be looking at. Okay, so we'll be look at the common source stage. This is one variant, common source stage with current source load. Okay, so remember the gain of a simple common source stage is given by this equation if channel length modulation is not neglected. We also remember that if we construct a circuit like this, so V in here, V out here, and this current source is constant and ideal. So if it's ideal, we analyzed this last time and we saw that the gain was equal to minus GM times RO, right? In a sense, what happens is that this current source has replaced this RD. The current source, an ideal current source, has an infinite impedance because it's an open circuit. So RD goes to infinity and we end up with minus GM times RO. That is the highest voltage gain we can achieve from a single transistor. So if you compare this topology with this topology, what we see is that RD simply reduces the gain, right? So I would like to not have RD, and that's why I replace this RD with the current source to maximize the gain. Now, unfortunately, we cannot buy an ideal current source. We have to go and see how we can implement it. And we just saw, well, we can implement it like so. Which one of these should I put there? Well, I have a current source that is injecting current into a node. Right? It's pouring into a node. So we have to go and see which one of these two can do that. This cannot do it because it draws current from the node to ground. But this one can push current into the node. So we have to go for this topology. All right, so let's go and implement it. We go ahead and say a realistic implementation would be like this. The current source will be realized by a PMOS device with some sort of bias connected to its gate source voltage. And then our input device, this guy here, if I call it M1, and that's our amplifying device. And this is really the best we can do for now in terms of approximating that circuit, right? That circuit is approximated by the circuit here. So we'll call this M2. This is what we call a common source stage with current source load, because this load is no longer a resistor, but an actual current source, an approximation of a current source. Okay. So we would like to find the voltage gain of the circuit. Now, the best we could do is this, but that was with an ideal current source. With a real current source, the gain is probably not that high. It will be lower. So let's see what we get. All right. Well, if I draw the small signal model of the current source, what do I have? Well, I just remember that the small signal model of this whole thing is just a resistor that goes to AC ground. So I can say that this is equivalent to RO2 and then M1. So we have the input and output here, and this goes to AC ground. Now don't panic. I'm mixing things up here, right? I'm drawing this part of the circuit as a small signal model, but not this part. I just kept it like that. It's okay. We should be comfortable with these things. Sometimes if you replace everything with small signal models, it's just too crowded. It's not easy to see things. So we just look at it like this, because this is actually quite close to this circuit, right? The only difference between this circuit and that circuit is that RD is replaced with RO2. So we can write the voltage gain of that circuit on the far right from this expression. right? I don't need to draw the small signal model of M1 and solve the circuit again. So I can say that AV now for these circuits is equal to minus GM of the amplifying device. This is the amplifying device, right? Because it receives the signal and produces the signal. So minus GM1 times the total resistance tied between the drain and AC ground. So here we have RO2 going to AC ground. We also have RO1 going to AC ground because the source of the device is at ground. So this would be RO1 in parallel with RO2. So that is the voltage gain of a common source stage with a current source load. Our hope is that this value is greater than this value, meaning that we can build a current source, that M2, whose output impedance, RO2, is greater than what we can have with a resistor. Okay, and that circuit has many applications in circuit design, this one. All right, so that's what we call a common source stage with current source load. All right, so that's one example of how we can play with the common source stage and create interesting variants. All right, let's, of course, one assumption here is that both of these devices are saturated in saturation. So in saturation, and sometime later we should see how we can ensure that, but for now we just accept that they are both in saturation. Very well. Before we go to the next common source variant, I need to talk about another type of device, a two-terminal device approximately, that is also useful. We have developed a current source using a MOS device. And that current source has a relatively high impedance. RO is considered a relatively high number. All right, so the next device that we will look at is called a diode connected transistor or device. So the term diode connected comes from bipolar technology and bipolar days, but we just take the term as is. We don't worry about the terminology too much. So a diode connected MOSFET is as follows. You take a MOSFET, for example, an NMOS device, and connect its gate and drain together. That is called a diode connected MOSFET. How many terminals do we have here? Well, we have two terminals, provided that we don't worry about the effect of the substrate. Remember, I always said in this course we don't worry about the substrate and the fact that the substrate acts as a fourth terminal on the device. So we don't worry about that here. Okay, so it's a two-terminal device. All right, so maybe, again, from the perspective of small signal modeling, it can be modeled by a resistor. So let's see how that comes about. How do we analyze this? Well, we have to draw the small signal model and see what we get. For general applications, we don't have to neglect channel length modulation. So let's include that and proceed and see how far we can go. All right, so here's how it goes. We draw the small signal model of the circuit. We have V1 and then GM V1 just for the basic transistor. Then we have its output resistance RO, and what we observe is that the gate and the drain are shorted. So the gate and the drain are shorted. Two wires are sticking out, these two wires, and we would like to find the impedance between these two wires or these nodes. So we follow the procedure. We come up from outside, apply a small signal voltage Vx, knowing that all independent sources are set to 0 here. And we connect it to these two wires of interest and measure the resulting current. Vx over Ix is defined as the impedance that we see between these two nodes. And what we are thinking is that perhaps this two-terminal device will lend itself to a simple resistance as far as the small signal model is concerned. Maybe, maybe not, right? So let's proceed and see what happens. Okay. All right, so in this calculation, we need to look at the circuit carefully. As usual, we would like to eliminate V1 because V1 eventually should not appear in Vx over Ix. Do we know the value of V1? Yes. If you start from here, the voltage difference between these two wires is Vx, and we just travel this way, we see that the voltage difference between these two is still Vx. It's just a single wire going from here to there, another single wire from here to there. So this is Vx. So V1 is equal to Vx. Okay. That means GMV1 is equal to GMVx. Let's write a KCL at this node. Ix is coming in, and out of that node go the current through RO. How much is the current through RO? We have Vx over RO. So Vx over RO plus this current, right? These currents flow out of this node. GMV1, which happens to be Vx. So this tells me that Ix over Vx, oh, actually I needed the other way around. Let me erase this. So this tells me that Vx over Ix is equal to, we have 1 over RO plus GM. That's a nice little equation that we have. In fact, we can even make it simpler. We have the inverse of the sum of two conductances, two inverse resistances. So that says that this is equivalent to the parallel combination of two resistances. So this is equivalent to RO in parallel with 1 over GM. 1 over GM is resistance, some resistance, and RO is some other resistance. This parallel combination is the same as this. Okay, so that's very easy to remember. In fact, what this tells us is that if I sit here and I look this way, I have RO in parallel with something else, 1 over GM. So that means that what's left over, if I don't worry about RO, must be 1 over GM. In other words, if, for example, RO is infinity, meaning channel length modulation is neglected, the impedance seen between these two terminals is equal to 1 over GM. So that's a good little rule to remember. If you have a diode-connected device and we neglect channel length modulation, the impedance between these two is 1 over GM. Or even if GM is much greater than 1 over RO, or RO is much greater than 1 over GM, then again, the impedance we see between these two is just 1 over GM. So 1 over GM dominates in this impedance, and it's a relatively low impedance level. So by contrast, here we had a relatively high impedance level. A current source gave us RO, a diode-connected device gives us 1 over GM, approximately, or 1 over GM in parallel with RO. So that's also a good rule to remember. This topology can be easily applied to a PMOS device as well. So it will look like this. Again, out of habit, I draw the source terminal on top of the page. You don't have to. The source terminal can be on the bottom as well. The key point here is that for diode-connected device, we need to connect the gate and the drain together. The gate and the drain. However you want to draw it is fine, but you have to make sure that the gate and the drain, not the gate and the source, must be connected to each other. All right, so that's what we call a diode-connected device. It has a relatively low impedance, 1 over GM or 1 over GM in parallel with RO. Very well. Now that we have this device, we will build the next type of common source stage. So let's go ahead and do that. Let me draw a line here. We call this CS stage with, not surprisingly, diode connected load. Right? That's very natural to call it. So you can guess what that would be. I will take a common source stage and replace its load resistor with a diode connected device. So let's go ahead and do that. Here's a common source stage. That's the input device. V in, V out. That's the definition of a common source stage, right? And now we need a load to connect to VDD because the bias current has to flow. So what kind of load should I use? Well, I tried current source before. Now I will try a diode connected device. Which type would I use? Either one is fine. You can use either one. Not a big deal. Sometimes we use a PMOS device. Sometimes we use an NMOS device. So let me show you an NMOS device for now. So the gate and the drain are shorted together, and they are connected to VDD. The source is available, and that connects to our circuit, just like this resistor. This resistor goes between the drain and VDD. This two-terminal device also goes between the drain and VDD. That is a common source stage with diode connected load. As usual, we would like to find the voltage gain. Okay. So again, I'm too lazy. I don't want to draw the small signal model of everything. So I would like to see, based on my previous results, can I just write out the gain equation? Now for simplicity, let's assume lambda is equal to 0. And let's proceed. Okay. Well, if lambda is 0, the diode connected device can be approximated by a resistance. A resistance, we calculated this resistance, and it's just equal to 1 over GM because RO is infinity. So this guy can be replaced by a single resistor equal to 1 over GM. And we give these names, so M1 and M2. So this circuit now looks like this. We have 1 over GM2 and the input transistor. And we call this M1. And lambda is 0 for both devices. Now, we are familiar with this circuit because that just maps to this. And if channel length modulation is neglected, we don't have that. So we just say G minus GM of the amplifying device times the resistance tied between the drain and AC ground. So the voltage gain will be equal to minus GM1, GM of the amplifying device, times the resistance tied between drain and AC ground, which is only 1 over GM2 because we don't have RO1 since lambda equals 0. So that's just times 1 over GM2. Very simple. So interestingly, the voltage gain of a circuit is the ratio of two GMs. Now you may say, what's the big deal? Well, actually there is something interesting about that. For that, I will write in these GMs in one of the three forms that we saw before. Remember, each GM of a MOSFET has three forms. So let's write this out like this. We're going to write this as minus, and GM1, we know that is equal to 2 times mu n C ox times W over L times ID. So that's 2 mu n C ox W over L of 1 times ID 1. That is GM1. Similarly for GM2, we have 2 mu n C ox is still an NMOS, so that becomes mu n C ox. W over L2 ID2. So look at these equations for a second and see what kind of result we can get. It's actually quite interesting. Well, we see that a bunch of terms cross out. Mu n Cox, 2 mu n Cox here, 2 mu n Cox here. ID1 and ID2 are also equal. It's the same current flowing through them, the bias current. So ID1 and ID2 also fall out. So the beauty of this circuit is that its voltage gain is given by the ratio of W over L's of the two devices only. It doesn't depend on anything else. So let me write that here more clearly. It's equal to W over L of 1 divided by W over L of 2. Now, why is this interesting? Well, in the original circuit, we see that the voltage gain has some dependence on Gm. And Gm has dependence on many things. On the bias current of the device, on mu n Cox, mu n is mobility is a function of temperature, and so on. So this voltage gain is not very stable. It may change with various environmental changes. Whereas here, we don't have any dependence on the current or the mobility, for example. So we see that it's only a function of some geometrical constants. W is how wide the device is. L is how long it is. And these things don't change much. So when we look at W over L of 1 divided by W over L of 2, that's a relatively constant number as the environmental factors change. So this gives us a more stable voltage gain than this circuit. That's why this circuit is attractive, at least with the approximations that we have made so far, meaning lambda equals 0. Okay, so now, what if lambda is not 0? I will give you 90 seconds, and I want you to find the voltage gain of the circuit assuming lambda is not 0. That's the quiz of today. Okay, so what does your answer look like? Well, to solve the circuit with lambda not 0, we just need to remember two expressions. One is the gain of the common source stage, like so, minus Gm times the total resistance tied between drain and AC ground, and this equation for the impedance of a diode-connected device if lambda is not 0. So remember these two and go to the next page and see what happens. Okay, so here's the circuit. And we simply model these as we know them. So this time I will replace M2 with a more complete model including channel modulation, including RO. So that's what I get. I have M1, and now here I have two impedances in parallel. 1 over GM2 in parallel with RO2. And that goes to AC ground. This is the impedance that we found for a diode-connected device, including channel length modulation. Okay, so again we proceed with the general equation of a common source stage. We say AV is equal to minus GM1, because this is the amplifying device, times all the resistance that we see between the drain and the source, and the drain and the AC ground. So that's 1 over GM2 in parallel with RO2, in parallel with 1 over GM, parallel with RO1. So 1 over GM2 in parallel with RO2 in parallel with RO1. All those three impedances appear between the drain of M1 and AC ground. So that is the voltage gain of the circuit with channel length modulation included. Of course, if channel length modulation is negligible, we go back to where we were before. Very well, so much for the common source stage with a diode connected load. Now we are ready to look at one more concept. Well, last time we talked about the concept of port impedances, and we have a procedure for calculating these things. Now, we apply that to the common source stages that we have studied so far. In particular, we are interested in the input and output impedances of these circuits. So I'll explain what that means, and I'll try to find it for all these stages that we have analyzed recently. All right, so we're going to look at input and output impedances. Well, the procedure is the same as before. We don't have many new concept here. Here's a common source stage. This is the input port, this is the output port, right? We measure the output voltage from here to here. We apply the input voltage between here and here. To find the input impedance, this is what we do. We set all independent sources to 0. So this becomes 0, AC 0. We come from outside, because we are interested in the input impedance, we apply a voltage source between the input terminals, or to the input port of the circuit. So that is Vx, and this should be Ix. Vx over Ix in this arrangement will give us the input impedance of the circuit. Okay, so how much is that? Well, fortunately or unfortunately, the circuit is very simple. We know that the gate of a MOSFET is insulated from the channel, so the gate doesn't draw any current, any significant current, at least at low frequencies. There is a capacitance between the gate and the channel, Cox, remember? We had that, but not for low frequency calculations. So it's very simple. We say input impedance, which is equal to Vx over Ix in this arrangement, is equal to infinity at low frequencies. Okay, so that's very simple. All right, how about the output impedance? All right, so for the output impedance, this is what we do. We take the circuit, we identify the output port. These are the output port nodes. We come from outside and apply a voltage source. Of course, before that, we set all independent sources to 0. This is 0. And this is also 0. Why? Because ordinarily, we drive the input of the circuit by a voltage source. So because that voltage source has to be set to 0, it's independent, this becomes a short circuit. And now we connect this here we measure Ix, and that is the output impedance of the circuit. So it's a critical distinction here. It's not really a fundamental distinction, but so that we keep track of what we are doing between these two. In this circuit, when we measure the input impedance, the output is not shorted because we do not have a voltage source connected between these two. Right? We only measure this voltage. We don't apply anything to it. Whereas in this case, when we are looking at the output impedance, this input is shorted because in reality, this input is driven by a voltage source. The voltage source is applied to it. So we have to remember these things. Okay, so how much is the output resistance here? Well, we may or may not know. We can draw the small signal model of the device very quickly and see what we get. Here it is. We have V1, GM V1. Let's be more general and include the output resistance of the device. And then we have RD going from here to AC ground, which is the same as here, right? So RD also goes from here to ground. And now I'm applying my voltage source between these two, trying to measure this current. The key point here is that I have set the input voltage source to 0, so that's a short circuit. Okay, so again in this case it's simple enough that we don't have to go and write KVLs and KCLs. We see that V1 is 0 because we deliberately shorted it. That means that the bias of course is there, but we do not allow the gate source voltage to change with time. So this is 0, the current doesn't change with time, that's 0. So all is left is our RO and RD, and they are in parallel. So the output impedance of the circuit is equal to RO in parallel with RD. If we neglect channel length modulation, it's just RD. So that's the resistance that we see at the output of the circuit. We use this term to see a resistance, and by that we just mean when we apply this Vx, and apply this Vx, how much is Vx over Ix? In this case, we see infinity. In this case, we see RD in parallel with RO. Okay, so from now on, oftentimes, in addition to the gain of the circuit, we also try to find the input impedance and the output impedance of the circuit. Because eventually, these play a role when we try to build more sophisticated circuits. Very well. So, this is the output impedance for a very simple common source stage. Now, how about the other two types that we introduced? Well, let's quickly look at those. So, I will write this as I/O impedances. I/O means input and output. Input and output impedances of the other two types. So, we had a current source load, for example, like so. Remember, we had a PMOS device approximating a current source. How much is the input impedance? Same as before, infinity at low frequencies. So that's gone. How much is the output impedance? The output impedance consists of, again, remember that for output impedance calculation, this VGS is set to 0. This VGS is set to 0 because these are all independent values. Okay, so what remains is this. Let's draw the circuit quickly. It's a good practice for us to draw the circuit. Let me change the color of my pen also. Okay, so we have the source of this device, and we have a current source going this way called GM2 V2, and V2 is between here and here. That is the model of the PMOS device with RO2 included. And this point is AC ground because VDD becomes AC ground for small signal analysis. And because we're setting all independent source to 0, this gate source voltage also goes to 0. because it doesn't change with time. So this also becomes a short circuit. We have taken care of the top of the circuit. Now let's take care of the bottom of the circuit. The bottom of the circuit, we have the same situation. So we have GM1, V1. And V1 is the gate source voltage for small signal analysis. Then this goes to AC ground. And again, because the gate source is driven by an independent source, independent voltage source, it has to be shorted. And then we have the output resistance of the device, RO1, and these are actually the same node because they are connected. Here's the node. And we would like to find the impedance between this node and ground. So we come from outside, apply our own voltage source. We call it Vx, and measure Ix. Okay, now the circuit is actually quite simpler than it looks because V2 is 0, right? The gate source voltage does not change with time. So GM2 V2 is 0. Similarly, V1 is 0. So GM V1 is 0. So what do we have left? We have from here RO1 going to ground, RO2 going to ground. So we just say Vx over Ix is equal to RO1 in parallel with RO2. That was simple enough. That is the output impedance of a common source stage with a current source load. The input impedance is infinite. Okay, the third stage that we analyzed was a diode connected load. So it looks like this. Diode connected means the gate and the drain are shorted. So that's what we have. Again, the input impedance is infinite. We don't worry about it. We just look at the output impedance. Okay, so let's quickly figure out what that is. Again, let's stay general if we can. So lambda is not 0. If lambda is not 0, we know that the diode connected device from the previous page is equivalent to 1 over Gm in parallel with RO. So what I have here is 1 over Gm2 in parallel with RO2. That's for M2. Nothing else. It's a two-terminal device. It can be represented by a two-terminal resistor. How about M1? Well, if you like, we can draw the model of M1, but quickly see how it reduces to something simple. We have V1 here, but V1 again is shorted because the voltage source driving the gate source of M1 is independent, so it must be set to 0. And this goes to AC ground. These are the terminals of interest, this terminal and this terminal. So we come from outside, apply our own independent source, Vx, and measure the resulting current. Okay, V1 is 0, this current source is 0, that's gone. What do we have? From here to ground, we have RO1. From here to ground, we have 1 over Gm2 in parallel with RO2. So we say that the output impedance of the circuit is equal to RO1 in parallel with 1 over Gm2 in parallel with RO2. We also note that even though we have 3 resistances in parallel, there's one that's dominant, this one. But this is typically quite smaller than these two. So the overall output impedance of the circuit is approximately, roughly, equal to 1 over Gm2, because that's quite smaller than the other 2 resistors. Okay, so that is the output impedance of this stage. Very well. Okay, so we have one more variant of the common source stage topology to look at, which we call the common source stage with source degeneration. But before we go there, I would like to talk about an issue that we face in circuit design, in particular with respect to the common source stage. So let's go back to this page that we had before and remember what the expression is for the common source stage voltage gain. It looks like this, right? Okay, well, both GM and RD, even if we don't worry about RO, both GM and RD are not very stable values. There are certain factors that can affect GM and RD. They can vary their value. These factors include a whole bunch. We have temperature, we have supply voltage, we have process, and then we have signal level. So that might look very complicated, but we'll go through each of them carefully. So let me try to redraw this on the next page. Assume for now no channel length modulation and just focus on these two factors and see what we get. All right, so we're going to go there and so we call this the problem of gain variation. Okay, so here's the situation. We have a common source stage, very simple, and without, if lambda is 0, without channel length modulation, the voltage gain is given by minus GM times RD. Now remember that GM itself has different expressions. For example, it's given by 2 mu n C ox W over L times ID. Okay, so we have several different types of variations that arise. What that means is that when I design the circuit for a gain of, let's say, 5, and I actually build it and I go measure it, I may get different numbers. And we'd like to see why. All right, so there are the following factors. So factors affecting the gain. Okay, so the first factor is temperature. Mobility of electrons and holes in silicon is a function of temperature. So when we go to higher temperatures, the mobility drops, and overall the GM drops. So if you build a circuit, an integral circuit, and you test it in a very hot climate, for example, Saudi Arabia, or in a very cold climate, like in Norway or one of those countries near the North Pole, or north of Canada, for example, then you get different results because mobility changes. So we have temperature as one factor that affects our results. And as circuit designers, we have to take care of that. When we design a circuit, the circuit has to work for a very wide range of temperature. For example, from 0 degrees centigrade to, for example, 80 degrees centigrade. So across this whole range, the circuit has to be acceptable in terms of its performance. Okay, the next issue is supply voltage. Supply voltage. Now that eventually translates to this ID. This ID, as we will see later, eventually depends on the supply voltage. Now the supply voltage may vary. Why? Well, when you charge up your cell phone, it is the battery is charged up to, let's say, 3.6 volts. But as the battery discharges, the voltage comes down to maybe 2.5 volts. So your circuit must be able to operate acceptably at a supply of 3.6 volts all the way to a supply of 2.5 volts. And if such a supply variation results in a large variation ID, then GM varies too much, the gain varies too much, that's not good. So that's the other factor we have to worry about. All right, the third one is what we call process variation. And process, in our thinking, means that, remember, we have these wafers on which we build these devices. So the foundry service that produces these wafers, that builds these wafers every day, build thousands of these wafers every day. Now, the problem is that when you design a circuit, when we design the circuit and implement it on a wafer that comes out today is a little different from the wafer that comes out tomorrow. In what respect? Well, sometimes the mobility is not quite the same. Sometimes the threshold voltage is not quite the same. So this circuit has to work, has to give us proper gain, even though with the process these things are changing. The mobility, even at a fixed temperature, will not be the same from this wafer to this wafer, from this chip to the next chip. So we have to take care of that. All right. And there is one more, which we call signal level. And that's a more subtle situation. So let's talk about the signal level and see what that means. For that, I have to draw a couple of waveforms. So let's change the color of our pen to green and see. All right, so here's the situation. We have let's plot for this device. Remember, we have a microphone and then we have a battery. Maybe this color is too light, so let's change to blue. Okay, so remember that we have a battery here of value, for example, V0, and then we have a microphone. So if I plot VGS as a function of time, if the microphone produces no signal, the VGS is just V0. So we have a constant voltage for the gate source. But then when the signal comes in, VGS goes up and down like this. Okay, that's good. How about the drain current? So the drain current as a function of time, in the absence of the signal from the microphone, is constant. So again, it's something like this, ID0. But when the VGS goes up and down, the current also goes up and down, so the current goes like this. So no problem. Ordinarily, when we perform small signal analysis, or when we say we have small signal operation, the assumption is that this change in the current is negligible with this much, with respect to this much. Meaning that the change in the drain current is negligible with respect to the bias value. Okay? And that means that ID is relatively constant. ID here is about the same, equal to ID0. We use that for our GM calculations. That's good. But now, let's suppose something like this happens. So let me change the color to red. Suppose that this microphone, suddenly I'm speaking very loudly into the microphone, so I end up with a large signal here. Okay, so now what happens? Well, the drain current also undergoes huge fluctuations. So drain current also goes like this. So now we have a problem. We see that here, the drain current is very high. Here, it's very low. So if I go ahead and calculate GM according to this equation, GM is higher here than here, which means the voltage gain of the circuit is higher here than here. The voltage gain of the circuit is changing with the signal level. Right? The signal goes up, we have, for example, higher gain. As it goes down, we have lower gain. And that's undesirable because it distorts the signal. If you give it a sinusoid at the input, you don't get a sinusoid at the output. You can see that the positive peaks of the sinusoid experience more gain. The negative peaks of the sinusoid experience less gain. So that won't be a nice symmetric sinusoid anymore. There's distortion, and we would like to avoid that. So we see that the voltage gain of this circuit, this very simple circuit, can vary according to all of these parameters. So next time we will look at a circuit that tries to reduce the effect of these parameters upon the gain. I will see you next time.